Hi everyone, welcome to August's virtual lecture. I'm Carla Gonzalez and I'd like to introduce you to Kristofer Davis, who will demonstrate how to invert TEM data using Geoscience ANALYST Pro Geophysics. If you have any questions during the presentation, don't hesitate to type them into the Q&A. And just a reminder that this webinar is being recorded and it will be in our YouTube channel in the coming days. And that's it for me. Go for it, Chris.
Thanks, Carla. So today I'll be showing some time domain EM data. We'll be starting from a curve, which I will show, and then we'll work our way up to running an inversion with VPEM1D. So here I've actually been given some data in a workspace file, and as I expand some of these folders, you can see that there's a file icon next to it. So here we're dealing with some paleo channels, and if I just double click on this this file, what this is showing is we're here in Australia, and we're looking at these paleo channels within the Lindsay East Paleo Valley. So this is kind of our area of interest total, and we're just going to look in this area. And so here we see that we have both the paleo channel drainage and where they actually think they are right here. And beyond that, we have some, let's see, we have some DEM data. So here we're going to actually zoom in, and we'll just look at a small chunk of this. And we have some SkyTEM data. So let me click on that. And what we're looking at right now is actually the MAG data. So we're looking at the TMI, and we have this bedrock stratigraphy that strikes mostly east-west. And although some of the paleo channels are defined and controlled by this bedrock, the main ones, as you can see, are actually north-south, and so they cross-cut the bedrock strike. Within this curve here, this is my EM data as well. So not only do I have the TMI, you can see I have all these channels. So I have low moment Z, high moment uncertainties that were given to us, high moment Zs, X, etc. In 4.0, each one of these guys with the little tables is a group. So you could always group data, but now you can see them. So if I wanted to look at just the high moment Z, I can actually use this as a filter, and now it shows me all my high moment Zs, and we can then just work our way through and actually visualize the data. So as the title of the talk states, we're going to look at some EM1D inversions. Just to be able to keep it short, I'm gonna actually downsample this data to begin with. This data is a curve. Although it was already in, it could have come in from another workspace. I could have also brought it in as a Geosoft database, a GDB, or even a TEM style file. But regardless, it's a curve. So there's nodes, and it's joined by segments. So let's say we're interested in just this area here. What we're going to do is go ahead and downsample it. And here we're going to downsample, and we're just going to pick an area of interest. Let's say we do something like that. So everything outside of the grid I'm going to discard, and then I'm going to keep my lines intact, which basically means instead of bringing points and getting a point, because I'm going to keep about a point per cell, but rather than keeping just the points, I want to make sure that the point per cell is along the line. And we're just going to do 250 meters, and let's just call this downsampled. So of course, when we discard locations, we don't delete it, we just create a new data set, which is what we've done here. So now we have this downsampled data set with all the data that we had before. And you can see we still have honored where the original lines were. And then just in this case, we have a long line about 250 meters of downsampling. So now we have this downsample data. What we really want to do is create an EM data set. So a curve is very generic in Geoscience Analyst. However, if we have an EM data object, it has certain characteristics such as waveforms and channels that come with it. So to do that, we'll go to Geophysics, create EM dataset. And here's the different types of data sets we can create. So this is a time domain. I need to select what my input is, whether I have both transmitter, receiver, just transmitter. In this case, they're coincident, so I don't have to worry about it. I'll just keep it as receiver, and I'll go ahead and do the downsample data with a loop radius. The rest of this is basically offsets for the transmitter, so that will be 0. As of right now, we could just go ahead and create data based on this data table. If we didn't have data and we just want to create a forward model, we could do it from the load system menu here. But the thing is I really want to use only some of the high moment Z. I'm going to want to get rid of a few of the channels. So what I'll do is I'll go to this group and manage the data groups. And let's just do the high moment Z. And we're just going to do the later channels. So what I'm going to do is go to the high moment Z, and let's just pick 13 through 38. I'm just going to hit apply. And now I've made a property group, and you can see that property group is now here as well. So then I'll say, no, the property groups I actually want to deal with is this high moment Z later. And if you see that the table is not there, this is because this high moment Z, these two groups are actually different lengths. So they have different number of components. So as soon as I unclick that and I only have one, it's happy again. So now what I want to do is I want to put in some times. I could go through and start to just simply type in times. But here, this little icon will allow me to load from a Maxwell channel file. So I'll click on that, and I'll choose my channel file. And you can see it's automatically loaded it in. And channel files by standard should be milliseconds, although I know this is microseconds, so I have the opportunity to change it here. But since this is a lecture, I'll go ahead and accidentally hit confirm in view. And what this is doing is it's now created both a transmitter and a receiver object that are linked. The EM data comes in, and you can see that we have receivers in the metadata, transmitters, the survey type, the unit type, which is really important. We have some things, the channels, for instance, and then the groups that are considered EM groups, and a waveform because it's time domain. As I had mentioned, I didn't switch it to microseconds. So what we can do is look at the channel values in units. And this will give me an opportunity to update these channel values if I was wrong when I imported them or created them the first time. Or I can just simply say, no, actually, this is microseconds. And you can see that the unit now has changed to microseconds. Since it is time domain, I need a waveform. So I'm now going to go to create edit waveform. And this has a couple simple styles. So here in the red is the current, the normalized current in amps. So it's from 0 to 1. Later in 4.1, we will be dealing more with the 100% duty cycle. So right now, it's just simply turn on, turn off. The normalized response is in the teal here. So basically, this actually isn't any data per se, but this is the location of our data channels based on our timing marker T0. So as soon as the current is shut off, this is where it is. So if I wanted to put some on-time channels, I'd just change the timing mark, and that would allow it to be on time as well. Here we have another little icon, and this is to load an ASCII file waveform. And I happen to have a high moment waveform. That's just a simple ASCII 2-column file. And when that comes in, it will say, this is basically the preview to make sure everything's okay. It will normalize the current for you if it's not. So if it sees that the current is over an amp, it'll normalize it. And then it just wants to make sure that the time is correct. So this is correct, it is in seconds, but if I happen to have the waveform in milliseconds or whatever, I could change that. And as soon as I hit OK, you see that it's now adjusted it, so I can see that waveform. And that's going to be a quote unquote custom waveform. So now in 4.0, anytime you save your waveform, it is actually saved behind the scenes. So even if I went to say a half sine and started to change things, if I go back to that custom, it's exactly what I, in this case, loaded in or what I had saved. So hit OK. And now I have a waveform. And the waveform, you can see the timing mark, and I have all of my currents and my times. And these are all in microseconds, but not to worry. If you're ever exporting the EM data, say for UVC, it will convert it to seconds, so you don't have to worry about it. And same with the EM1D, it will take care of the actual units. The next thing I need to do is for an inversion is apply some uncertainties. So there I'm going to go to create channel-based uncertainties. It's going to ask me what my groups are. And in this case, it's HMZ later. That's my data. I have two types of percentage that I could look at. So I could do just the straight percentage of the datum. So in other words, if it's 5% and I have a datum of 100, my uncertainty will be 5. Or I could use the percentile. So I could, put the 5th percentile, 95th percentile, and choose it that way. The global floor is, let me bring that down to 3%. The global floor is actually in your data units. So in this case, my floor might be 0.001. If you have small data, you can always put 1 e to the -3, for instance. You can basically put a single floor. And then the output name will be what I'm going to call it. So let's call it the high moment Z uncert. Now, with each one of these components or channels, I should say, of the data group or the data type, I have the name of them as found in the tree. So for each one of these, it's just going to use the global percentage and the global floor that I gave it. If I'm finding that one is more noisy than the other, I can always uncheck this link and then go ahead and change it. So then if the floor is changed, this will stay the same. So this actually allows you to micromanage as much or as little as you want when you're creating your uncertainties. Same with the floor. And the reason why we do the percentage plus a small floor or the percentile is to make sure that it's proper. The other thing I will mention is that our uncertainties, when we use the percentage, it's the higher of the percentage or the floor. It's not the addition to. So in this case, the floor is purely for what we would consider an effective 0, just to make sure we're not overweighting those. If I hit apply, I now have this uncertainty, and that's where that is there. And just to show real quick, if I have this downloaded, so here we have the X component. I have the Z, but just to show you, if I go through and find that HMZ, I could actually go and say, okay, well, where's my uncert? HMZ is something like that. And then I could see how it goes. You could also view in the profile viewer, you could actually view as the array of channels. So now I have my uncertainties, my waveform, everything is set from the data perspective. Now I need a model. Currently, to create a model, we'll need at least 2 surfaces. Here we have the cover. So I brought in the DEM as a 2D grid, and I created the surface by right-clicking the contextual menu, create surface from data. So I have some type of DEM above, and then below, about minus 200 meters of elevation, I have some cover. So I'll just go to the VP Model Designer. I'm going to select on the, let me just hide that a second. I'm going to select on my data, and you can see this is what, this will be my outline. So here are my 2D prism outlines, potentially. I'll put out the DEM, and then I'll put the surface at the cover. And this will be the simple two layer. I'll hit create. Okay, and with each model comes a unit. So for instance, I have property, but I could call that conductivity. And this conductivity, we'll just set a very simple 0.1 and 0.1. And then we'll go ahead and create the upper bounds and lower bounds right now. So lower, upper. And so for each unit, I'll simply say lower bound is 0 and an upper bound of 5. And this is all in Siemens per meter, by the way. So that would give me a simple one. I could do a homogeneous inversion at this point just to see what the best is for the cover. But what I'll do is I will go ahead and go to this VP utilities and create some heterogeneous units. So what I'm doing is basically subcelling this cover unit into smaller cells. So I select the cover. Let's do 10 meters, and let's expand in depth by 20%. We're just going to call it the heterogeneous model. And there we go. We now have the same unit. However, if I go to cells, you can see now it's nice and subcelled like that. And then if I look at the conductivity, you can see the conductivity is also now 0.1 and 0.1. So here, now we're actually ready because we have an upper lower bound conductivity and a VP model to do an unconstrained inversion. So we'll just do geophysics, VPEM1D, and this is called a heterogeneous inversion. As you can see with VPEM1D, just like VPMG, we can do geometry inversion. So we could actually create this 2-layer and assume 2 different conductivities and do an inversion and move the base layer. We could do a homogeneous, so basically do a bulk property inversion of conductivity as well. So there's 3 panels when it comes to the heterogeneous inversion. We're going to need the points, the data, its uncertainty, and then we have some system parameters, and it all really depends on what your data type is. Is it PPM, DBDT, B field? We do have some simple systems to help you, so I'll just click on that and load. And that says, oh, I see that you're doing picovolts per meter to the 4th. We have dimensional DBDT, vertical component, coincident. We have a 10.36 radius, and then the transmitter pulse is 5,000 microseconds and 25 hertz. And then we're going to do the heterogeneous with the property, the lower and the upper bounds. And then we do 15, let's do 15 iterations. We'll bump it up. We'll go 25 iterations and 15%. We could solve all layers at once, and this is quote unquote fast. It's much faster than normal, but what it will do, here, let me just do this heterogeneous response. we'll hit apply. And then what I'll say is what VPEM is doing is it's actually going to solve for the first layer of cell, and then we'll go to the next one and the next one and the next one. And then it'll repeat that for no more than 25 iterations per prism. If you have any questions about the VPEM 1D code, this question mark here will bring up the actual VPEM 1D manual as a PDF. It's also available under the help in Pro Geophysics.
Well, there is a question in the meantime, if you want
Can I
to
verbally repeat how to get to the uncertainty assignment GUI? Sure. So the uncertainties for EM data are under the contextual menu of EM, of your EM data. So you can right click on your receiver. You'll go to create, because you're going to create EM based uncertainties or channel based uncertainties. And what that will do is allow you to create those uncertainties per channel all at once. So yeah, so remember, everything is a contextual menu, basically. There are very few things that are not. So if you're ever wondering what you can do with a object, just right click on it. Okay, so now I have the inversion, it's done. I'll just show the console here. So we did 8,000 cells. We had a misfit of 1.1 e to the fifth. So pretty big, and it's gotten down now to 2.9 e to the 2, so not too bad. And if I look at the inversion result here, what I'll do is, let me click on this guy. I'll put the Z section on, and this is in this is right now in conductivity color scale. So maybe what we should do is let me just go to the data colors, and I'll flip them. And then let me also do this. There we go. So now this is blue is high conductivity, low resistivity. So there you go. So now you can see that we have the we have this channel going through here, even at this this very downsampled simple inversion. The other thing I'll show is not only do we have that, so we have this het inv, and that has now created this guy. But if we go to the sample data, we also have the predicted data with all of its channels. So if we were to look at, say, the decay curve and select the downsampled receiver, and let's do the HMZ and the heterogeneous curve. So this is basically the predicted and the observed, and then do that. So, and then this will just go through the node selection, so you can see how well we've actually fit the data. And then this is just because the transition, but we want the transition to be a bit better. There we go. So you can see we do have negative data. We're not going to fit that with EM1D. So it just gives you the rest of that part there. And then if I go back to the viewport, you have the blue there, but let me just put receivers, but I can hit control and select a few different ones, and they will show up in the decay curves for both the predicted and the observed. So both the predicted and the observed are for each decay is the same color. Lastly, let's say we wanted to take that original inversion and do a geometry inversion. So if I went to VPEM1D geometry inversion, you can see you'd have to do it all over again, which is kind of a pain. So what I would suggest is there's a save and a load button down here. You can save the heterogeneous inversion. Just call it heterogeneous inversion. Hit save. And then you can come here and you can actually load the heterogeneous inversion aspect of it. And what this will do is copy everything that was in already. And a lot of it is actually the same. So the difference here is I don't have active units because I'm doing a heterogeneous this was heterogeneous, where here I need more homogeneous. But I can go back to the 2-layer, hit the conductivity property, and now I'm off and running with the geometry inversion. I can just hit apply and OK. When setting up the, so now I'm going to go to the Q&A. I'm basically done. I won't run the geometry inversion for time, but when setting up the inversion parameters, how can you control how much conductivity depth the inversion will recover using the later channels, or is the recovered depth not controlled by the inversion? So there's no soft constraints, so I can't push anything too hard. What I can do is I could give it different data sets, right? So so I didn't show it, but I downsampled this data set, but actually I could create an EM data set from a subset of channels. So let's say I created my EM data set. I could actually have my early channels and my late channels and my mid channels, and I could actually look at different parts of the model that way without just throwing it all in at once. So hopefully that answered that question. Can we run VPEM 1D outside of Analyst, just like we can with VPMG? You will be able to in 4.1. So not right now in 4.0, but in 4.1 with Pro Geophysics, you will have the opportunity to run it outside of Analyst, both locally on your machine and on a server as well, if you're running any high performance computing servers.
Cool. If there's anything else, feel free to add more questions in there in the Q&A or raise your hand. If you ever think of a question later, you can always email support@geoscience.com and we'll get back to you on that. And there is another question there, Chris. If you already have a cover thickness or basement topography layer, could you bring that in as surface?
Absolutely. So what you can do is when you create your model, that is where your geology that you know or think know will go. So if you had an actual thickness of cover, you could create, as long as you could create a surface from it or have a surface from it, you can absolutely create that layer in there. And with that, you can actually do a whole bunch of different things as well. Things like pierce point constraints or heterogeneous constraints, if we have them. You can do it that way, and then you can also just keep them. Basically, keep the cover thickness as it is, and then solve for it. Either through bulk property or trying to subcell at that point, or geometry for that matter. Can you generate a surface from a curve object like a DTM within the curve EM? So the curve object, so if you had a curve object, there's a couple ways that you could create surfaces. You could go to create surface from nodes, which is just a very simplistic creation of a surface. You can also use those nodes if you were to create through the surface designer, which requires a closed curve. However, you could use the nodes. Let me just bring that up a second. You can use the nodes as controlled points. If you had a DTM, okay, so if you had a DTM within the object, which is I think is what I'm specifically getting asked here, what I would suggest is putting it onto a 2D grid, which is not a problem. You can either minimum curvature or just straight up transfer the data, and then from a 2D grid, you can always create a surface from your data as well. So there's actually a few ways to create surfaces if you have that information on the curve. And remember, you also have scripting available in Pro. So if you need to add your altimeter data to your DEM to get to your proper Z of your receiver, you can do that as well.
Okay, so it seems like that's it so far, and you can still type it in while I just do the end speech here. But in the next few months, we're actually going to be changing our formula. So every other month, we're going to continue with these live lectures where we showcase some technological advancements. And on the other months, we're going to be releasing how-to videos showcasing a step-by-step approach to various tasks in Geoscience Analyst. which will also get uploaded to YouTube. So that's going to be slightly different. And in September, what we're going to put out is a video on how to visualize drill hole data in Geoscience ANALYST version 4.0. Just see if there's anything else in the Q&A.
One last question. It was kind of it's a little bit of a left field, but that's okay. I'll answer it anyway. The question is if we can invert magnetic data from a grid. And the answer is we can. You can put a grid into VPMG to invert. It will take the X, Y, Z coordinate of the grid value itself. So if the grid actually needs to be on a DEM, the best thing to do is actually create a node from cells, which is new in 4.0. And in that case, you could either put a draped height or you could put the elevation, and that's going to be this elevation here. And then you basically decide if you want a points, or you can put a curve in the U or V, and that will allow you to create that curve and then look at the profiles along that curve as well.
All right, cool. Well, if there's ever anything else, you can always send us an email at support@mirrorgeoscience.com. Otherwise, for today, I think that's it. So have a super great day, and yeah, talk to you guys soon.